Hello everyone, this is Jesse Crawford with Tarleton State University, and this is going to be our second video for Chapter 3 of the Foundations of Mathematics course, which is going to cover equivalence relations. This is going to pick up right where we left off last time when we were discussing relations, and I think a good way to get started today would be to look at some of the examples that we discussed last time. So the first one we looked at was if x and y are real numbers, we can say that x is equal to y, in which case x and y are related by the equality relation. Or we might say that x is less than y, where we're dealing with the less than relation. Or we might say that an integer x divides an integer y, where we're doing the divisibility relation. Or we might even have something like a triangle T1 is congruent to a triangle T2. So this would be the congruency relation for triangles. Now, last time we showed that formally a relation is a set of ordered pairs. But we also saw that working with relations as sets of ordered pairs is kind of cumbersome. It's not the most efficient way to do things. So a more efficient notation that we can use is we can say that a mathematical object x is related to a mathematical object y by the relation R. Now, something that is really pointed out by these first four examples is that every relation has a domain where it is applicable. So for example, if we're looking at x is equal to y, we might be talking about real numbers. If x is less than y, we might also be talking about real numbers. But if we have x divides y, this relation doesn't make a lot of sense for arbitrary real numbers. And in fact, we've always restricted the domain of this relation to be the set of integers. So the domain of this third example would be the integers, and the domain of this fourth example would be triangles, right? So what happens more generally is every relation has a domain A. So A is a set, and the elements that we care about are always elements of that set. So when we say that x is related to y, we have to assume that x and y are elements of A. And again, just for brevity, I'm going to put x and y are in A. So once you have a domain A and you have elements x and y that are in A, then it makes sense to talk about whether x is related to y or x is not related to y. So with all of that in place, let's actually take a look at what an equivalence relation is. So this is the definition we're going to be working with here. It says, let R be a relation. We say R is an equivalence relation, provided it is reflexive, symmetric, and transitive. So any relation that has these three properties, reflexive, symmetric, and transitive, is an equivalence relation. Now, what are these properties? Well, we actually looked at these last time, right? And so this is the page in our slides where we went through and defined formally what all of these properties are. So as a quick recap, what does reflexive mean? Reflexive means that for any element x of your domain, x is related to itself. What does symmetric mean? Symmetric means that for any two elements of your domain, if x is related to y, then y has to also be related to x. What does transitive mean? We're all familiar with this property for a lot of the relations we've studied, like equality and less than. It would say that for any three elements x, y, and z in your domain, if x and y are related, if x is related to y and y is related to z, that implies that x is related to z. That's what transitivity is. So right off the bat, those three conditions that we care about, reflexive, symmetric, and transitive, we can realize that these middle two relations will not qualify as equivalence relations. And the simple reason they don't qualify as equivalence relations is because they are not symmetric. So symmetric says that if x is related to y, then y has to be related to x. And we kind of talked about this last time. So for example, we said that 2 is less than 5, but 5 is not less than 2. So the less than relation is not symmetric. And because it's not symmetric, it's not an equivalence relation. The divisibility relation is also not symmetric. You might say, for example, that 3 divides 15, but 15 does not divide 3. So the divisibility relation is not symmetric, and therefore divisibility is not an equivalence relation. So I'm just going to go ahead and delete these two. The other two examples we have here are equivalence relations. I'm not going to give a formal proof of either of these facts because we will actually write a formal proof that a new example is an equivalence relation in a minute. But, it can be helpful for us to just verify that these are equivalence relations, just sort of quickly check that they satisfy the properties here. So the way you want to think about that is just imagine the relation R that you have and just replace it with the relation that you're thinking about. So let's say we want to verify that equality is an equivalence relation. Just imagine if there were an equal sign here. This would say for every x in A, and in this case, the domain A is the real numbers. That's what we're talking about. So for every real number x, is x equal to x? And the answer is sure, that's true. So this is reflexive. Is it true that for any two real numbers x and y, that whenever x is equal to y, that y is equal to x? That is true. Is it true that whenever x is equal to y and y is equal to z, that x is equal to z? Yes, that is true. And therefore, the equality relation is reflexive, it is symmetric, it is transitive, and therefore it is an equivalence relation. What about congruency? So if you imagine taking this relation is congruent to, and you replace R with that. So that would say for any triangle x, is x congruent to itself? And the answer is sure. Yeah, that's true. Is it true that if x is congruent to y, then y is congruent to x? That is true. Is it true that if x is congruent to y and y is congruent to z, then x is congruent to z? Yes, that is true. And so congruency is a transitive relation also. So I actually have a picture of three congruent triangles here. And we can, quickly verify that they are congruent. You'll notice that every one of these triangles has one side that has a length of 2, the other side has a length of 1, and they're all right triangles. So by the Pythagorean theorem, the hypotenuse for each one of these is the square root of 5. So therefore, by the side-side-side condition, these are all congruent triangles. So that condition says that if two triangles have the lengths of the triangles are all the same, then by the side-side-side condition, those two triangles are congruent. Now, I want to distinguish slightly between something, we can say that two triangles are congruent, but they can actually be different triangles. So for example, this red triangle and this blue triangle, they are different in the sense that they have different locations in space and they are oriented differently. So for example, the red triangle has its right angle at the origin, 0, 0. The blue triangle has its right angle at the point 5, 0. The red triangle has this vertex pointed to the right, the blue triangle has this vertex pointed to the left, and the green triangle is oriented in a completely different way, and it's in a different location in space. So these triangles, they're all different in the sense that they're composed of different sets of points, and they occupy different positions in space, but they are also congruent, and so even though they're different triangles in one sense, they are also in a sense equivalent. And this is really the goal of equivalence relations. It's the idea that on the one hand, two objects are technically different, but on the other hand, they are equivalent in some way, and we want to be able to speak about the way that they're equivalent in a mathematically rigorous way. And again, this picture might also help to see that all these properties are satisfied. So for example, every one of these triangles is congruent to itself. And you can have things like if the red triangle is congruent to the blue triangle, then of course the blue triangle is also congruent to the red triangle. And we could talk about transitivity and so on. So this is a good example of equivalence. Now, today we actually have a completely new example of an equivalence relation, which is this middle definition here, congruency mod n. Let's actually read what this says. So this says, let n be a positive integer. We say that the integers x and y are congruent modulo n, and we write x is congruent to y mod n if n divides x minus y. So before we try to write some formal proofs involving this relation and talk about it in an abstract way, let's just kind of do some examples just to get a feel for this. I'm going to do some examples where I let n be equal to 5. We can just do congruency mod 5 and see what that looks like. So for example, I claim that 7 is congruent to 12 mod 5. Now, is this really true? Let's check. What do we actually need to check? Well, the definition says that x is congruent to y mod n if n divides x minus y. So the thing that we actually have to check here is whether 5 divides 7 minus 12. Well, is that true? Yeah, sure it is true, right? Because 7 minus 12 is negative 5, and 5 does divide negative 5. So this is actually a true statement. 7 is congruent to 12 mod 5. What else can we say? Well, I claim 7 is also congruent to 37 mod 5. Okay, let's check to see if that's true. Is it true that 5 divides 7 minus 37? And the answer is, yeah, that's true, because 7 minus 37 is negative 30, and 5 does divide evenly into negative 30. So that is also the case. What are some other quick examples we could do? I claim that 6 is congruent to 31 mod 5. Let me put 31 here. So 6 is congruent to 31 mod 5. That would mean that 5 divides evenly into 6 minus 31. And that's true, because 6 minus 31 is negative 25, and 5 divides evenly into that. And it's also true that 6 is congruent to 46 mod 5. And that's because, if we think about it, 5 does divide evenly into 6 minus 46, because 6 minus 46 is negative 40, and of course 5 does divide evenly into negative 40. So all of these are examples of congruency statements that we can make. Now, there's actually something else going on here. All we've really done here in each one of these cases is applied the formal definition from over here, and that's fine, but there's actually a quicker way to think about this. So it turns out that two numbers are congruent mod n if and only if you get the same remainder when you divide each of them by n. So let me see how to sort of show that for these examples here. So in this case, the examples that we're looking at here are n is 5. So let's say we do 7 divided by 5. What is that going to be? Well, we're going to get 1 remainder 2, right? What if we take 12 divided by 5? Well, in that case, we're going to get 2 remainder 2. What if you take 37 divided by 5? Well, 37 divided by 5 is going to be 7 remainder 2. So what we're seeing here is, if you take the number 7 and divide it by 5, you get a remainder of 2. If you take the number 12 and divide it by 5, you get a remainder of 2. Well, then that means that 7 and 12 are congruent mod 5. If you take the number 37 and divide it by 5, you also get a remainder of 2. So 7 is congruent to 37 mod 5. So if you get the same remainder, when you do the division, those two numbers are going to be congruent. So I did some examples with 6 down here. I talked about 6, I talked about 31, I talked about 46. Well, let's do those calculations. What is 6 divided by 5? Well, that's going to be 1 remainder 1. What about 31 divided by 5? 31 divided by 5, that's going to be 6 remainder 1. What about 46 divided by 5? 46 divided by 5 is going to be 9 remainder 1. So what happens is, if I take the number 6, the number 31, the number 46, if I divide any of these numbers by 5, I get a remainder of 1. And what that means is that 6 is congruent to 31 mod 5, 6 is congruent to 46 mod 5. And for that matter, you might be wondering, well, what about like 31 and 46? Are 31 and 46 congruent? And the answer is, yeah, they are. 31 is congruent to 46 mod 5. Why is that true? Well, is it true that 5 divides evenly into 31 minus 46? And the answer is, yes, it is, because 31 minus 46 is negative 15, and 5 divides evenly into that. And so this is actually a good example. We're about to see that this is an equivalence relation. And basically what we're seeing here is the transitive property. If 6 is congruent to 31 and 31 is congruent to 46, then 6 is congruent to 46. This is an example of transitivity. Or an example of, let's actually just talk about that now. I mean, I think we get the point here. Let's actually go through and see, just again, by example, we don't need to write this out mathematically yet with a formal proof, but let's just see, does this relation appear to be an equivalence relation? In other words, does it appear to be reflexive, symmetric, and transitive? We can just do some quick examples. So for example, is the number 7 congruent to 7 mod 5? And the answer is, well, we need to check, does 5 divide 7 minus 7? And of course it does, because 7 minus 7 is 0, and every integer divides evenly into 0. So this is true. Another thing we could look at is, a minute ago, I said that 6 is congruent to 31 mod 5, and we actually checked that that was true, because again, 5 divides evenly into 6 minus 31. But we might also ask ourselves, well, is 31 congruent to 6 mod 5? Does this work? And it does, because 5 does divide evenly into 31 minus 6. So 31 minus 6, that's going to give us positive 25, and 5 will divide into that. So right here we have an example of reflexivity. Again, what does reflexive say? Reflexive says that every element is related to itself, right? So this is what reflexive says. For any element of our domain, that element is related to itself. And here we see an example of that. 7 is related to itself. 7 is congruent to 7 mod 5. Symmetric says that when x is related to y is related to x, and we have an example of that here. 6 is congruent to 31 mod 5, and 31 is congruent to 6 mod 5. So this is an example of that. And again, a minute ago we had an example of transitivity where we wrote that, I think we wrote that 5 is congruent to 31 mod 5. You can check that, we've already checked that. And 31 is congruent to 46 mod 5, and we've already checked that. And it does turn out that 5 is congruent to 46 mod 5, and we can easily check that. So we have a situation where because x is related to y and y is related to z, it follows that x is related to z. That's an example of transitivity, and we have that here. 5 is related to 31, 31 is related to 46, and therefore 5 is related to 46. And that's a transitivity example. Okay, so we've looked at several examples here that just kind of show that it seems like congruency mod n is an equivalence relation. We've written some examples here that seem to show that. But we know that just writing down some examples cannot actually prove something to be mathematically true in general. But we do have this proposition at the bottom that says congruency mod n is an equivalence relation. Let's go ahead and prove that now with a rigorous proof. Okay, let's go ahead and write that out. Okay, proof. So we want to show that congruency mod n is an equivalence relation. And the important thing to realize is there's 3 things we need to check. We need to show that congruency mod n is reflexive, symmetric, and transitive. We need to show these 3 properties. So let's just do each one of these one at a time. Okay, so first we'll look at reflexive. Okay, so what do we need to show to prove that something is reflexive? So we need to show that, and now let's go back to our definition of what reflexive is. We need to show that for any x in our domain A, that x is related to itself. Now, the first thing to realize is when you're talking about congruency mod n, you're only talking about integers. So the domain that we're looking at here is integers. So we need to show that for any x in z, I'm just going to use a capital Z here for the integers, I need to show that x is related to x. But again, I'm not going to write r because I actually have a specific relation in mind. The relation that we have in mind is congruency mod n, okay? And actually, let's start this proof off at the very beginning by just saying, let's let n be an integer. So we just kind of have an integer that's fixed throughout this entire proof. But we need to show that for any x in z, that x is congruent to x mod n. All right, well, let's show this. Okay, so we have a universal quantifier here. This says for any x in z, so we know how to handle a universal quantifier. We're going to let x be an arbitrary element of z. And then we need to check that x is congruent to x mod n. Well, what's the definition of that? The definition of that is that n divides x minus y. So an interesting thing about Notepad here is I can kind of write where my goal is. My goal is I want to say that n divides. See, what I actually want to say is I want to say that x is congruent to x mod n. That's our goal, right? So this is what the proof template would say. We want to say that for any x in z, x is congruent to x mod n. How are we going to do that? To handle this part of the proof, we let x be an arbitrary element of z, and then our goal is to get here, right? So I'm just going to write this at the bottom. Now, what would establish this? Well, what would establish this is simply saying that n divides x minus x. Okay? So by this definition over here, if n divides x minus y, that's what it means for x to be congruent to y mod n. So if n divides x minus x, that's what it means for x to be congruent to x mod n. So we need this to be true. Maybe we can back up a bit. That's the same thing as saying that n divides 0. Okay? And then the question is, does n actually divide 0? Well, it does, right? Because n times 0 is 0. And now we've sort of done this by using logic that's backwards in a way, but now if we read this forwards, this proof is completely valid. So we can say, let x be in z. Well, is n times 0 equal to 0? Yes, that's true by appendix D. Does that mean that n divides 0? Yes, by definition of divisibility. Well, if n divides 0, does that mean that n divides x minus x? Yeah, because x minus x is 0 by appendix D. So this is by appendix D also. But if n divides x minus x, does that mean that x is congruent to x mod n? Yes, because that's the definition of congruency mod n. And there we go. We have a proof now. So we let x be an arbitrary element of z. N times 0 is 0. That's just a basic fact of the integers that we have in appendix D. That implies that n divides 0 by definition of divisibility. Because x minus x is 0, that implies that n divides x minus x, again by appendix D. And then that means x is congruent to x mod n by definition of congruency mod n. But now notice what we've done. We've taken an arbitrary element x and z, and we've shown that it's congruent to itself mod n, but that's what it means to be reflexive. So the conclusion here is that congruency mod n is a reflexive relation. Okay, let's show that congruency mod n is symmetric. Okay, let's think about what we need to show. So we need to show that for any x comma y and z, that if x is congruent to y mod n, then y is congruent to x mod n. Okay, so again, if you ever get lost on what is our goal right now, our goal is to show that congruency mod n is an equivalence relation. An equivalence relation is a relation that's reflexive, symmetric, and transitive, so we have to show that all of these are satisfied. We've already showed that it's reflexive, so now we're trying to show that it's symmetric. So if you get lost and you're like, yeah, I'm not sure what symmetric means, you just have to go back a couple slides, right? This slide says that something is symmetric if for any elements of the domain, whenever x is related to y, y is also related to x. And that's what we have here, right? For any x, y in our domain z, the integers, if x is congruent to y mod n, then y is congruent to x mod n. So this congruency mod n is our relation right now. So that's what we need to show. Okay, well let's tackle this with our proof template approach. So we need to handle this universal quantifier. So we are going to let x and y be arbitrary elements in Z. Now we have to handle an if-then statement, right? We know how to handle an if-then statement. We assume the thing on the left, and we need to deduce the thing on the right. So now we're going to assume that x is congruent to y mod n. And our goal is we want to eventually get down to something that says y is congruent to x mod n. That's our goal. That's what our proof template is telling us to do. Well, let's see what we can do immediately below this line. We know that if x is congruent to y mod n, by definition, that means that n divides x minus y. So let's just write that down. N divides x minus y by definition of congruency mod n. Okay? Well, what does that mean? If n divides x minus y, what does that mean? Well, that means that n times some integer a is equal to x minus y, right? So by definition, and I'll say for some a in z, by definition of divisibility, right? So that is actually what that means. Okay, but if n times a is x minus y, then something that's pretty natural to do here is to say that n times negative a is equal to negative x plus y. And all we've really done here is multiply both sides by -1. So this is just by appendix D. So appendix D allows us to do this kind of basic algebra in arithmetic, right? And then, of course, we can also rewrite this as n times negative a is equal to y minus x. And this is also just by appendix D. Appendix D says that addition is commutative, so we can rewrite this, rewrite the order of this. But actually think about what we've said now. We've said that n times the integer negative a is equal to y minus x. But that actually means that n divides y minus x. And lo and behold, if we now consult the definition over here, x is congruent to y if n divides x minus y. Well, that means y is congruent to x if n divides y minus x. And that's exactly what we have here. N divides y minus x. Therefore, y is congruent to x mod n. So again, to recap, we started off by assuming that x is equal to congruent to y mod n, and we've concluded that y is congruent to x mod n, and that establishes that congruency mod n is a symmetric relation. So now we have congruency mod n is a symmetric relation. All right, so again, our goal here is we want to prove reflexive, symmetric, and transitive. So far, we've done reflexive and symmetric. Let's look at transitive. Okay. So for transitive, we need to show, and again, if you ever forget, we can just go back, right? So transitive says that if we take 3 arbitrary elements of our domain, so in other words, if we do for any x, y, z, and again, we got to keep in mind, our domain right now is the integers, right? For any x, y, z in the integers. Let me bump this down here. So for any x, y, z in the integers, we need to show that if this condition holds, then this condition will hold. So we need to say if x is related to y and y is related to z. Okay, well, what does related mean? It means congruent. X is congruent to y mod n, and y is congruent to z mod n. Then, right, because this is an implication symbol. What this entire thing says is if this stuff is true, then this condition is true, right? So that's what we're doing here. If x is congruent to y mod n and y is congruent to z mod n, then we need to show that x is congruent to z mod n. That's what we need here. Okay, so if we want to prove that congruency mod n is transitive, this is what we need to show. All right. So let's start parsing through this with our proof template. So first thing we need to do is handle our universal quantifier right here. We need to let x, y, and z be arbitrary elements in the integers. Then we need to handle our if-then condition. To handle an if-then condition, we assume the stuff on the left. So we're going to assume, and actually we have a nice little copy-paste here. Let's go and just utilize that. There we go. Okay, so let's assume the stuff on the left there. And our goal is to show that x is congruent to z mod n. That's the goal that we ultimately want to get to. Let's just start writing some stuff down here. So we know that x is congruent to y mod n. Again, that's what this says. So that's equivalent to saying that n divides x minus y. So we know that n divides x minus y. And we also know that y is congruent to z mod n. So that tells us that n divides y minus z. And these are both by definition of congruency mod n. Okay, so we know both of those facts. But we know how divisibility works. So how does divisibility work? If n divides into x minus y, that means that n times a is equal to x minus y for some integer a. And we also know that there's some integer b, n times b is y minus z for some b and z. But if that's true, then we can simply add those two equations together. So now we can say that NA plus NB is equal to x minus y plus y minus c. So just the basic fact that if two equations, if the left-hand side of an equation is equal to the right-hand side, and then that's also true for another equation, that you can add both left-hand sides and add both right-hand sides. That's essentially a property of Appendix D. So we'll have by Appendix D here. Of course, at this point, we can factor out n, and we have a plus b. And then we can also realize that negative y plus y is 0, and then x plus 0 is just x, and we get this, right? And suddenly, this is this is basically more just sort of algebra. But basically, at this point, we have that n divides evenly into x minus c. So we can just write n divides x minus c. But that actually tells us that x is congruent to z mod n. That's the definition of that. So x is congruent to z mod n. So again, as a quick recap, we started off by assuming that x was congruent to y mod n and y is congruent to z mod n, and we deduced that x is congruent to z mod n. And that establishes that congruency mod n is a transitive relation. And now the overall conclusion that we can draw from all of this is we've shown that congruency mod n is reflexive, congruency mod n is symmetric, and congruency mod n is transitive. Then that means our overall conclusion is that congruency mod n is an equivalence relation. And we are finally done with that proof. Okay, so that's the end of that first argument. So that is like the first really mathematically substantial proof that we've given to show that something is an equivalence relation. And these are the kind of techniques you would have to use in general to do that. So what else is this proposition saying? It's saying some pretty basic stuff here. Saying x is congruent to 0 mod 2 if and only if x is even. I think we can just very easily show that. Let's just prove this real quick. So let's assume x is congruent to 0 mod 2. Well, that means that 2 divides x minus 0. But x minus 0 is x, so that tells you 2 divides x, and that tells you that x is even. Okay, so if x is congruent to 0 mod 2, then x has to be even, and it's pretty easy to check. You just go the other direction as well, and it'll be very easy to check that that also works. Let's assume that x is congruent to 1 mod 2. Okay, well then that means that 2 divides x minus 1. That means that 2 times a is equal to x minus 1 for some a and z. And that actually means that x is equal to 2a plus 1 for some a and z. And of course, that is exactly our definition of odd, so x is odd. So basically, yeah, that just shows that if x is congruent to 0 mod 2, then x is even. If x is congruent to 1 mod 2, x is odd. You would also, because these are if and only if statements, you would technically need to go in the other direction as well. I'm just going to omit that because we actually have a lot to cover for today's video, but in principle, that's what you would have to do. Now, what about some examples, though? I think some examples are in order here. If you just take, for example, the number 10, is 10 congruent to 0 mod 2? And the answer is sure it is, because if you take 2, does it divide 10 minus 0? It does. 10 minus 0 is 10. 2 does divide evenly into 10. Is the number 13 congruent to 1 mod 2? And sure, yeah, because 2 does divide evenly into 13 minus 1. And so 13 minus 1 is 12. 2 does divide evenly into 12, so that's true. So what we're seeing here is just, and you can check this for other examples, there's just this general pattern that every even number is congruent to 0 mod 2, every odd number is congruent to 1 mod 2. And this does go back into something that was said earlier, that if you take 10 divided by 2, what do you get? You get 5 remainder 0, okay? So every even number, if you divide by 2, you're going to get a remainder of 0. So all the even numbers are congruent mod 2. Whereas if you take any odd number, if you take 13 divided by 2, you're going to get 6 remainder 1. So the remainder that you get when you divide by 2 for an odd number is always going to be 1, and therefore all odd numbers are congruent mod 2. They're all congruent to 1 mod 2, actually. Okay, so with all of that under our belts, let's go to our next slide here. So this is our last slide, and this is going to get into an important concept of equivalence classes. So this is our definition here. This says, let R be an equivalence relation on a set A, and let little a be an element of the set A. The equivalence class of A, denoted bracket A, is bracket A is the set of all x in A such that x is related to A. Okay. So to get this sort of motivated, we're going to do a few proofs here with this notion of equivalence classes. But to get this motivated, let's look at some examples. So let's just say, for example, that we're looking at equivalence or congruence mod 3. Let's actually talk about what that is. Now, again, two things are going to be congruent mod 3 if and only if you get the same remainder when you mod out by 3. So for example, let's just talk about what is bracket 0 in this case. Bracket 0, by this definition, is the set of all x in the integers such that x is congruent to 0 mod 3. Okay? So the relation that we're talking about right now is congruency mod 3. And I just want to say for the number 0, what is its equivalence class? The equivalence class for 0 is the set of all variables x in the integers that are congruent to 0 mod 3. And it's pretty easy to write down what these are. Of course, 0 is congruent to itself mod 3. It's also congruent to anything else that's a multiple of 3. So, you know, it would kind of look like this. And it also goes back to negative numbers. So you would have things like, I'll just list these out, -9, -6, -3, and so on. Like that. So this is what this would look like. So this is what this equivalence class would look like. And it actually has infinitely many things in it. So again, just, you know, maybe if anyone's not convinced of this, like, is it really true that 0 is congruent to 9 mod 3? And the answer is sure, because 3 does divide evenly into 0 minus 9. And so that's actually the case. So basically, the reason this number 9 is in this equivalence class is because 9 is congruent to 0 mod 3. And the same thing is true for every other number in this equivalence class. If you take any of them, they're congruent to 0 mod 3. And again, another way to look at it is if you do 0 divided by 3, 0 divided by 3 is 0 remainder 0. If you do 9 divided by 3, that's equal to 3 remainder 0. So you might be thinking like, oh, it looks like all the numbers in here are just multiples of 3. That's true. So basically, something is going to be congruent to 0 mod 3 if and only if it actually is a multiple of 3. And that's why it looks like this. Now, what about bracket 1? What is bracket 1 going to look like? Well, it's going to follow a pretty similar pattern. So let's see. It would be, let me put -8 here, -5, -2, and then 1, 4, 7, 10, and so on. Now we can see in this equivalence class, you'll kind of notice in the first example that each pair of numbers here is separated by a distance of 3. Like the jump from 9 to -6 is -9 to -6 is 3, -6 to -3 is 3. These just keep going up by 3 every time. The same thing is true here, right? This is an increase of 3, increase of 3, increase of 3, and so on. It just keeps increasing by 3. And you know, I don't want to belabor this point too much, but just one more quick example. You know, someone might say, should 7 really be in here? And the answer is sure, it should be, because the question is 1 congruent to 7 mod 3? And the answer is that is true, because 3 does divide evenly into 1 minus 7, because 1 minus 7 is -6, and 3 divides evenly into that. But again, probably an even more insightful way to think about it is that 1 divided by 3 is 0, remainder 1, and 7 divided by 3 is 2, remainder 1. If you take any number in here and divide it by 3, you're going to get a remainder of 1, like 10. 10 divided by 3 is going to be 3, remainder 1. All of these things in this set have a remainder of 1 when you divide by 3. The last example I'm going to give here is bracket 2. Bracket 2 is the equivalence class of the element 2. It's the set of all elements in Z that are congruent to 2 mod 3. And this would just be -7, -4, -1, 2, 5, 8, 11, and so on. And so that is actually what that set would be. And again, you can just check for any 2 elements in this set, they are congruent to 2 mod 3. They'll also be congruent to each other mod 3. And every element of this set has the property that when you divide it by 3, you get a remainder of 2. If you divide 8 by 3, you get 6 remainder 2. If you divide 11 by 3, you get 3 remainder 2, and so on. All of these things have a remainder of 2. Now, the interesting thing about this example is that every single integer is in one of these equivalence classes. That's one thing, first of all, to notice. And you can actually see that, like, for example, in this case, every integer between -9 and 11 is somewhere in this picture. And of course, these dots keep going in both directions. So every integer has to be in one of these classes for a very simple reason. If you take any integer and divide it by 3, the remainder that you get has to be 0, 1, or 2. And so every integer is in here somewhere. So that's one thing to point out. Another thing to point out is that all of these equivalence classes are non-empty, so none of these are empty sets. And also, they don't intersect at all. They're completely disjoint sets. And in fact, that's what this proposition at the bottom says. It says that if you let R be an equivalence relation on a set A, then the equivalence classes are non-empty, pairwise disjoint subsets whose union is equal to the whole set A. So a nice picture of that would be to think about it this way. You've got this domain A. And again, the domain A, you want to think of it as like a universe. It's like this big set that has everything under consideration that you care about. And what happens is when you look at equivalence classes, you divide that domain into subsets. And these subsets are non-empty. Every one of these equivalence classes has something in it. These subsets are pairwise disjoint. Another word for pairwise disjoint is mutually exclusive. These equivalence classes do not overlap at all. Like if you look at the examples over here, it's not like you have the same number showing up in more than one equivalence class. That doesn't happen. Like the number 6 is in this first equivalence class. This number 6 is not in the other two, right? So they're pairwise disjoint. These equivalence classes don't share any points with each other. So like typically in a Venn diagram, those circles in a Venn diagram overlap and there's something in the intersection. In this case, that's not the case. So this class, and this class are totally pairwise disjoint. And then the third property is that every element of the domain is somewhere in one of these classes. In other words, if you take the union of all these equivalence classes, you get the whole space. Every element of A is somewhere in one of these equivalence classes. There are no points that are left out. And so that is the final proposition we want to establish for today. We want to prove that if we have an equivalence relation on a set A, the equivalence classes are non-empty, pairwise disjoint subsets whose union is the whole space A. We would like to do that. Before we can do that, though, we need to establish this proposition here, and that's going to allow us to prove this proposition, and it'll be nice and easy once we do that. Okay. So let's go ahead and prove this one. So what is this one saying? It says let bracket A be an equivalence class. First thing is that A is an element of bracket A. We need to prove that. And the second thing here is we need to prove that if B is an element of bracket A, then bracket A is equal to bracket B. Okay, let's do that. And in fact, I just realized I think I'm going to want these examples to be here. So let's go and leave these up. But yeah, let's prove these. Okay, the first thing we need to prove is we need to show so yeah, let's go ahead and let R be a equivalence relation on A. And so let's go ahead and let A be in A. So all of that is set up. So the first thing we need to do is we need to show that A is in bracket A. Well, this is really easy because A is related to A by reflexivity of R. So we know that R is an equivalence relation, right? If R is an equivalence relation, then R is reflexive. But if R is reflexive, that means that every element is related to itself. So A is related to A. But the definition of bracket A is the set of all x's in your set that are related to A. So if A is related to A, it follows that A is in bracket A by definition of bracket A, okay? So any element that's related to A, that's what this is saying, right? Any element X that's related to A is in bracket A. That's what we know right here. Okay. So what else do we want to show? We need to show that if B is in bracket A, then bracket A is equal to bracket B. Okay, we need to show that. All right, well, let's go ahead and assume that, okay. Okay, that sounds fine. Well, if B is in bracket A, again, by definition here, that means that B is related to A, right? So that means B is related to A by definition of bracket A. Okay, now we need to show at this point, so let me actually do this to make it clear that I'm sort of dividing this part up. So I'm trying to show that if B is in bracket A, then bracket A is equal to bracket B. We've already assumed this first part, right? We've already assumed that B is in bracket A. So we simply need to check that bracket A is equal to bracket B. We need to show that bracket A is equal to bracket B. And, you know, we need to keep in mind that bracket A and bracket B are sets, right? If we want to show that two sets are equal, we need to show that bracket A is a subset of bracket B, and we need to show that bracket B is a subset of bracket A. So that's everything we need to do here in order to establish this. All right, so let's go ahead and get started on this. Okay, so let me, if you don't mind, let me go ahead and I'll sort of focus in on this first statement first. I want to show that bracket A is a subset of bracket B, right? So I'm simply going to let X be in bracket A. Well, that means that X is related to A by definition of bracket A. Okay, that sounds good. Now, I want to point out that up here, we already assumed that B was in bracket A, and that says that B is related to A, but that also means that A is related to B by symmetry of R. And then you'll notice that if X is related to A and A is related to B, then that implies that X is related to B, and I'll just write out the full reasoning here. X is related to B because X is related to A is related to B, and R is transitive. So this is a property that R has. If X is related to A and A is related to B, then X has to be related to B because R is a transitive relation. But here's the thing. If X is related to B, that means that X is in bracket B. And so we've accomplished what we've wanted to here. We've let X be an arbitrary element of bracket A, and we've shown that X is in bracket B, and therefore we've showed that bracket A is a subset of bracket B. So that part of the proof is over. Okay. So maybe I'll even just put this here for emphasis because I have a feeling this might be getting a somewhat hard to follow. So let's just write that down. Therefore, we have established that bracket A is a subset of bracket B. Now, the other proof is basically exactly the same. So we need to show that bracket B is a subset of bracket A. How do we do that? Let's go ahead and let X be an arbitrary element of bracket B. That implies that X is related to B by definition of bracket B. But if X is related to B and B is related to A up here, right? That implies that X is related to A. So X is related to A because X is related to B is related to A, and R is transitive. That's all of the information you need to draw that conclusion. So again, we already said way up here that B was related to A, right? But we've also established that X is related to B here. So all of this is true, and now X is related to A, and that means that X is in bracket A. So if we think about what we've done here, we've let X be an arbitrary element of bracket B, and we've shown that X is in bracket A, and therefore we have shown that bracket B is a subset of bracket A. And now to wrap this up, if bracket A is a subset of B and bracket B is a subset of A, we can conclude that bracket A is equal to bracket B. And now we've really done what we've set out to accomplish. We set out to accomplish that if B is an element of bracket A, then bracket A is equal to bracket B. We started off the proof way up here. We assumed that B was in bracket A. We assumed that way up here, and we did all this work, and that did show that bracket A was equal to bracket B, and so we're done with this proposition. So yeah, this proposition is totally true. Now, you know, obviously we can do a mathematical proof, and that's fine, and It does rigorously demonstrate that the proposition is true, but it might still kind of feel like we don't have the most intuitive idea of what's going on. So let's actually look back at this example. I just want to point out that for this example, all of these conditions hold. So for example, this would say, for example, that 0 is in bracket 0. Is that true? And the answer is yeah, right? 0 is right there. So 0 is an element that's inside of bracket 0. What about 1? Is 1 in bracket 1? Sure. 1 is right here, and 1 is indeed in bracket 1, and 2 is in bracket 2. So all of these statements are true for this example that we just did. What about another statement? You know, this statement says that if B is in bracket A, then those brackets are equal to each other. So for example, 7 is in bracket 1. Does that mean that bracket 7 is equal to bracket 1? Is that actually true? And the answer is it is true, because let's actually write down what bracket 7 is. So bracket 7, by definition, is the set of all x and z such that x is congruent to 7 mod 3. So the important thing that we have to keep in mind as we're doing these proofs is we're constantly shifting gears between an arbitrary relation on a domain A. So this R, when I write R, I'm talking about a completely arbitrary relation on a domain A. That relation R might be congruency of triangles. It might be some other kind of equivalence relation on a different space, or it might be congruency mod n. So when we're doing a proof, like the proof we just did down here, we kept using the relation R to represent it's completely arbitrary. It could be any equivalence relation whatsoever. And our domain A is also an arbitrary domain A. Whereas right now I'm doing an example. I'm talking about congruency mod 3. That is my relation. And my domain is the integers. So notice here, I'm not putting x's in A. I put x's in the integer z. And here I'm not putting xr7. I'm putting x is congruent to 7 mod 3 because congruency mod 3 is the relation I'm talking about right now. But what we're trying to figure out right now is, according to this proposition, if B is in bracket A, it follows that bracket A is equal to bracket B. That's what this proposition says. And we notice that 7 is in bracket 1. So is bracket 7 actually equal to bracket 1? Let's actually check that. So bracket 7 is the set of all integers x such that x is congruent to 7 mod 3. Okay, well, let's think about what that condition would mean. So x is congruent to 7 mod 3 if and only if 3 divides x minus 7. But that's true if and only if 3 times some integer a is equal to x minus 7. This is kind of an informal argument, but just kind of writing this out. And then that's true if and only if 3a plus 7 is equal to x. Now, what is 3a? And again, a here represents an arbitrary integer. I really should have said that here for some a and z. So what does it mean to say that x is equal to 3a plus 7 where a is an arbitrary integer? Well, let's see what that looks like. Well, one possibility is that a is 0. So if a is 0, 3 times 0 plus 7 will give me 7. What if a is 1? I get 3 times 1 plus 7, I get 10. And then that will continue, right? Well, what if a is negative 1? If a is negative 1, I get negative 3 plus 7 is 4. What if a is negative 2? I get negative 6 plus 7 is 1. What if a is negative 3? I get negative 9 plus 7 is negative 2. What if a is, let's say a is negative 4. I get negative 12 plus 7 is negative 5. And then clearly I can do one more step. I can get negative 15 plus 7 is negative 8. And obviously that pattern will continue, and I can keep going backwards like that. And all of a sudden we realize that bracket 7 is equal to this set, but we've actually already shown that that set is this guy, right? That's what this is, which is bracket 1. So yeah, bracket 7 is literally equal to bracket 1. They're actually the same thing. And so just in general, if you have an equivalence class, like what is bracket 11? What is bracket 11 equal to? Well, bracket 11 is this equivalence class. It will be exactly the same thing as bracket 2. It will be the same set. So yeah, this proposition really is true, and these properties really do work in this way. Okay, so the last thing we want to do in these slides, and then we'll call it a day after we do this last proof, is we want to show that if R is an equivalence relation on a set A, then the equivalence classes are non-empty pairwise disjoint subsets whose union is A. So let's go ahead and run through that last proof here. Okay, so again, I'll break this proof into subparts. Let's do the non-empty first. So let's let C be an equivalence class. Okay, so right now you should imagine that C is a set, and that set is an equivalence class. Like one of these sets up here is an example of an equivalence class C. Now, if C is an equivalence class, then C must be equal to bracket A for some A in A. Okay, so for example, this is an equivalence class, right? Well, this equivalence class is equal to bracket 2. So if my equivalence class C is this thing, well, then it is equal to bracket 2. Every equivalence class is always equal to bracket something. So C is equal to bracket A for some A in A. But according to this condition over here, A is already always an element of bracket A. So A is always inside of bracket A, and therefore A is in C, and therefore C is non-empty. Okay, so that's the first thing we have here. Yeah, so basically I didn't put in all my justifications here. So let C be an equivalence class. Let C be an equivalence class. C is equal to bracket A for some A and A. This is by definition of equivalence class. A is in bracket A. This is by the proposition that we have here on this slide. A is in C, that follows immediately from the previous few lines, and C is non-empty, that just is basically by the definition of the empty set. So we are done with this part of the proof. Okay, let's show that these equivalence classes are pairwise disjoint. Okay, so pairwise disjoint is something that we went over in chapter 2. Basically, a collection of sets is pairwise disjoint if they don't overlap. Another way of saying that is that if you have two different sets and they're not the same set, then they don't touch at all. Their intersection will be empty. That's what we need to show. So let's actually write all this out. So let's show pairwise disjoint here. So let's let C1 and C2 be equivalence classes. Now we know that C1 has got to be equal to bracket A, and C2 has got to be equal to bracket B for some A and B. So that's just something to keep in mind. We'll use that in a second, but right now I want to write down, what does pairwise disjoint mean? We need to show that if C1 is not equal to C2, then C1 intersect C2 is empty. That's what we need to show. Okay, so that's what pairwise disjoint is. Pairwise disjoint says that if I take two different objects in my collection, in other words, if they're not equal, then they will not touch at all. They're mutually exclusive. So if C1 is not equal to C2, then C1 intersect C2 must be empty. They must be completely pairwise disjoint. This is what we want to show, this statement right here. Now, you'll notice that this is an if-then statement. It has an if here, and it has a then here, right? And as a quick reminder about if-then statements, there was something we talked about called the contrapositive. The contrapositive of the statement would be if, there's two things we need to do. So yeah, I think it would be helpful to just remind ourselves what this is. If I have a statement, if P, then Q, the contrapositive is if not Q, then not P, right? So what happens when you take a contrapositive is you change the order of the statements and you apply a negation to both of them. And it turns out what you guys showed in chapter 1 is that the contrapositive of the statement is equivalent to the original statement. So we can rewrite this statement here. We can take its contrapositive and it will say if, and I have to change the order, right? So this is going to this is going to move in front. If C1 intersect C2, but notice I have to negate it, right? So instead of saying is empty, I'm going to say non-empty. And then I'm going to take this stuff here, C1 not equal to C2, this part right here, and I'm going to move it over here. But again, I'm going to negate it. So now this is going to say then C1 is equal to, and in fact, we don't need to write it all out. We just say C1 equals C2. Okay. So yeah, if we take the actual thing we're trying to prove is if C1 is not equal to C2, then C1 intersects C2 is empty. That's equivalent to saying if C1 intersects C2 is non-empty, then C1 is equal to C2. The contrapositive is the same statement as the original statement. So we just need to show the contrapositive is true, and we're done with this part of the proof. Okay, well, let's do that then. Let's assume that C1 intersect C2 is non-empty. Let me just as a reminder mention that C1 is equal to bracket A and C2 is equal to bracket B, right? So that means if C1 intersects C2 is non-empty, that means bracket A intersect bracket B is non-empty. And that means there exists some C in bracket A such that C is also in bracket B. Okay, so there exists this common element that's in both of them, right? Now, if C is in bracket A, then that means that C is related to A. And this is just by definition of bracket A. If C is in bracket B, then that means that C is related to bracket B, or sorry, C is related to B by definition of bracket B. And another thing we can do here is we can say that B is related to C, and this is by symmetry of R. So again, the relation R that we're dealing with is symmetrical. So if C is related to B, then B is related to C. But now notice that B is related to C and C is related to A. So that means that B is related to A. And again, I'll just say it's because B is related to C, C is related to A, and R is transitive. Okay? So transitivity basically allows you to create this chain, B to C, C to A. That means B is related to A. But if B is related to A, that actually means that B is in bracket A. But actually, you'll notice over here in this proposition, we proved that if B is in bracket A, then bracket A is equal to bracket B. So now we know that bracket A is equal to bracket B by this proposition on page 8 of the slides. Okay, and also this, I didn't put my justification on this line. B is in bracket A by definition of bracket A. That's what that would be. Okay, so yeah, that's quite a long proof on that pairwise disjoint, but to kind of recap here, we took two completely arbitrary equivalence clauses, C1 and C2. We know that C1 has to be equal to bracket A and C2 has to be equal to bracket B for some A and B in our domain A. And what we're trying to show is pairwise disjoint. Pairwise disjoint means that if you have two different objects, they don't intersect, right? So if C1 is not equal to C2, they don't intersect. That's what we're trying to show. But that's really the contrapositive of that is saying, well, if they intersect at all, they have to literally be the same thing. That's another way of saying pairwise disjoint. The only way you can intersect is if you're the same set, right? You can't have two different sets that intersect because then they wouldn't be pairwise disjoint. So this is what we wanted to prove. We wanted to prove this contrapositive. So we started off by assuming the thing on the left. So we assume that C1 intersects C2 is not empty. Well, C1 is bracket A and C2 is bracket B. So that means that bracket A intersect bracket B is not empty. And that means there's some element C that's in both of those. There's some element C in bracket A that's also in bracket B. But the definition of bracket A is the set of all elements that are related to A. So if C is in bracket A, that means C is related to A. If C is in bracket B, that means C is related to B. And then from here on out, it was just a matter of getting this argument to finish up. So if C is related to B, B is related to C by symmetry. And that means you have a chain, right? Your chain is B is related to C and C is related to A. That means that B is related to A by transitivity, but that means B is in bracket A. And we've already established earlier that if B is in bracket A is equal to bracket B. So yeah, kind of a technical proof here. But yeah, that is actually a good way to wrap up that proof. Okay, the last part here. We want to prove that the equivalence classes have a union which is equal to A. In other words, if we take the union of all the equivalence classes in the entire space, that's going to be the entire space. There's nothing that gets left out. So let's actually prove this real quick. Okay. Okay, so a good way to get started on this, why don't we just give a name to the union? So let's just let U be the union of all the equivalence classes. Then basically we want to show that U is equal to A. We want to show that the union of all the equivalence classes is the entire space A. And of course, we know how to do that. We need to show that U is a subset of A. And we also need to show that A is a subset of U. Okay, let's go ahead and do this real quick. We know how to show subsets. We're going to let X be in U. Well, if X is in U, that means it's in the union of all the equivalence classes. And the way that you get inside a union is you have to be in one of the things that are being unioned. So if X is in the union, then it has to be in one of the equivalence classes. So if X is in U, then that means that X is in bracket A for some A and A. Okay, but let's actually think about what the definition of bracket A is. Bracket A is the set of all X in A such that X is related to A. So as soon as we've assumed that X is in bracket A, it automatically follows that X is in A. So we can just say that. We can just say X is in capital A by definition of bracket A. And we're done with that part, right? We just wanted to show that use a subset of bracket A, use a subset of A. Well, we've let X be an arbitrary element of U, and we've shown that it's an A. So that part's done. All right, let's go the other way then. So we need to show that A is a subset of U. So let's let A be in capital A. And we want to show that it's in U. And this is actually going to be pretty easy as well, because we can simply say A is in bracket A. How do we know that? Because of this proposition right here, right? A is in bracket A by the proposition. But if A is in one of the equivalence classes, it's clearly in the union of all the equivalence classes, and so that's it, we're done. So therefore, A is in the union of all equivalence classes. So as a reminder, if you have a whole bunch of sets, the union of all those sets is the set of all elements that you get that are in at least one of those sets. So if I'm trying to take the union of all equivalence classes, that's going to contain any element that's in any of the equivalence classes. So if something is in a single equivalence class, it's going to end up being in the whole union. So because A is in this equivalence class bracket A, it follows that it's actually also in the union of all the equivalence classes, and therefore A is in U. And so we've also shown that if we let A be in A, then A is in U, and therefore that shows that this thing is true. So we're basically done with this proof now. So we've showed that U is a subset of A is a subset of U, and therefore we have established that U is equal to A. And that's what our goal was. Okay, guys, this is a pretty long lecture, a lot of technical stuff here. These are the discussion problems. Again, I just want to invite you all to please feel free to ask me if you have any questions. If you get on any of these homework problems and you're having trouble, just feel free to email me a question, or you can also post a question in the homework and lecture help forum on Canvas. But that being said, I hope you have a great day, and I'll see you next time.